Thank you very much for coming this evening. Yes, so I'm Jon Carey. I'm the Associate Professor in Applied Geosciences here in the Earth Sciences department. I'm going to talk tonight about, this title is The Ground Shifting Under Our Feet, Understanding Landslides and Their Consequences. So just a bit of a broad introduction about myself. I started off in consultancy as an engineering geomorphologist, but way back when in 2002. And I worked there for around about 12 years. And during that time, I did my PhD part-time. And through that time, I worked on a lot of landslide problems, particularly in the UK, but also places like Hong Kong. I also worked in Shetland Islands and other places overseas as well. And in 2012, I moved to New Zealand and worked there in an organization called GNS Science, which I guess is broadly similar to the BGS here, the British Geological Survey. And there I worked on a lot of landslide problems, but working on things like the big earthquakes. So the Canterbury earthquake, I was there after that, looking at landslides associated with that. Then more recently, the Kaikoura earthquake, but also a lot of rainfall-induced landslide events as well. So doing a mixture of kind of research and kind of event response for big hazard events. And in that time, I've got to see a lot of landslides. And I'd say one thing that I think sometimes comes across, particularly in the media, that we sometimes kind of sort of like trivialize landslides. They become these things that are called slips. So we talk about floods and slips, and we think of them as these small kind of discrete events, kind of a bit of a nuisance, possibly a bit of an engineering problem. I'm here to try and get you to understand that that's really not the case. So this is probably the biggest landslide I've ever visited. This is the Daogong Bao landslide. It happened in 2008 during the Wenchuan earthquake in China, in the Sichuan province of China. It takes about 20 minutes in a vehicle to drive all the way from the toe of the landslide up towards the headscarf. So it's absolutely huge. It's a volume of about 1.167 billion meters cubed. So the little red arrow here is pointing to a research center that they actually built on top of the landslide debris. Because they wanted to study this site because it was just so big. And this is, you can see this really as a kind of landscape forming event. So you can see, beautifully into the mountain. The entire mountain has collapsed. You can see right into it. And this event has happened within seconds during an earthquake, where you've got a completely different landscape. So landslides are really can be really impressive. So why do we study landslides? Well, there's a number of reasons. One is that they're natural mechanisms that modify the Earth's surface. Their occurrence relates to a diverse and complex set of processes. And they're capable of affecting any landscape with relief. So if we think about seabeds, they can be kind of 2 degrees, and we still get these huge landslides sitting on seabeds. So they're kind of ubiquitous across the landscape. If you've got slopes and the right kind of materials, there's a chance that you can create landslides. And they have huge amounts of impacts. They impact property, they impact infrastructure, they have big impacts on the environment. And a real key thing is that there's a potential for them to increase into the future as well. So we've got, growing populations, people living in more kind of steep terrain environments, mountain environments. And we've got things like climate change and shifting weather patterns, which can, exacerbate landsliding as well. So there's a general belief that landsliding could increase into the future. And if we look at landslides on a kind of global scale, this is a paper back in 2018 by Frood and Petley. So they've kept a big landslide database of all the landslide fatalities across the world. So the figure here on the left-hand side is all the non-seismically induced landslides between 2004 and 2016 in their database. And you can see that landslides are a global problem, but they certainly happen in specific areas. So you can see things like the Himalayas here, obviously is a hotspot for landsliding into kind of the Pacific Rim kind of area here, India, and then obviously things like South America and the west coast of America. So broadly speaking, in locations where we've got large populations, tectonic activity, large rainfall, so things like monsoon rain, large rainfall, we typically get a lot of landslides, and as a consequence, we get a lot of fatalities associated with landslides. And in this paper, they showed that there was around about 4,862 fatalities between 2004 and 2016. 95% of those were single slope failures and 75% occurred in Asia. So you can see there's a real hotspot in Asia of where landslide fatality is particularly high. If we look at another location like New Zealand and look at the hazards there, New Zealand's really interesting because it has every hazard you could probably want. It has supervolcanoes, it has subduction zone earthquakes, it has tsunami risk, and obviously it has mountain environments with landslides too. And actually it's the most common hazard to affect New Zealand property and infrastructure. So they think the losses on an annual basis are around 200 to 300 million New Zealand dollars a year. And there's an average about 2 to 3 deaths per year. And that changes through time, but generally speaking, there's kind of this constant fatality, low-level fatality that happens. And around 700 deaths since 1840. So they cost the New Zealand economy about 250 to 300 million New Zealand dollars a year. And that's largely fixing assets, roads, bridges, the railway lines from landslides. But also things like loss of production from agricultural lands and damage to ecosystems as well. And interestingly, what we found in this data is that actually over this time frame, landslides have killed more people than any of the other hazards. So landslides have killed people more than earthquakes and more than volcanoes, which is quite impressive. But I think the thing is that obviously we don't kill many people in one go. So you know, in an earthquake you have multiple fatalities. So obviously that, you know, it's a lot more shocking. It's a lot more newsworthy. But actually landslides that, you know, kill a lot of people. And they can be either rainfall or earthquake induced in New Zealand. And you expect a significant rainfall induced landslide event, probably one a year. And when it comes to earthquakes, around about 10 a year. And obviously that changes. And we're talking about kind of magnitude, upper magnitude 6, magnitude 7 type earthquakes, which cause big landslides. So just what is a landslide? Well, a landslide is a mass movement. It's a mass movement of rock, soil, or debris, and it's moving down a slope. But there's many different styles and types of landslides. So landslides can rotate. So particularly if you have homogeneous materials, so all the materials are the same, you tend to see rotational style landslides where you get a kind of semicircular shear surface at the base of the landslide, and it kind of scoops out. When you've got kind of more stratigraphy kind of sloping, you see more translational landslides. So you see movements kind of translating down slope. And we also see things like block slides where we get these detached blocks that move on these discrete surfaces or on contact surfaces between two different types of material. And then when we look at harder materials, we can have things like falls and topples. So we see rock falls happening where we have really steep cliffs and you know, lots of fractures in the rock. Topples tend to be when you get overhanging rocks that can fall forwards. And also when we have a lot of water and very soft sediments, we get things like debris flows and debris avalanches and earth flows, which are kind of more muddy materials. So we get a lot of different types of landslides, and they're actually a really important part of hill slope geomorphology. They're a really important process in kind of how landscapes form. So, you know, we have these landforms, and because we have these landforms, we can look at the processes and materials within them. And from that, we can start to infer the kind of mechanisms that are causing the landslides. And then if we can understand the mechanisms that are causing landslides, we can look at things like the future behavior, how they might behave into the future, and start to think about the potential impacts that they could have. So here's just some examples. These are kind of looking at rock and debris avalanches. The picture here on the left-hand side is in New Zealand. This is something called the Lake Gun landslide. It's an ancient landslide that's been there, you know, thousands of years. Almost certainly, we think created by a large earthquake in Fiordland. But this is a huge rock avalanche that's happened. It's obviously gone right across the valley, blocked the valley. So we now have this lake here, which is called Lake Gun. So that's why that's the Lake Gun landslide. So the landslide's created a whole different environment. It's created a lake, and that's pretty much currently a permanent change in the landscape caused by that landslide. On the right-hand side here is another avalanche, which is the Viant landslide disaster that happened in 1963 in Italy, killed around about 2,000 people. So these are really big, avalanching, deep landslides that move really quickly and can cause a lot of damage. But obviously, you know, when you see these in the landscape, you have to think about how long they've been there. You know, how could they move in the future? What kind of events are required to move them? And that gives you a really good understanding of what kind of risk they potentially pose. At a kind of another level of scale on steep slopes, you can get things called debris flows. So this photograph here on the left-hand side is of a debris slide in Scotland. You can see that it's incredibly shallow, incredibly thin compared to what we were just looking at before. And it's got a very clear kind of debris flow track and a long run out and a kind of deposit at the base. So these are much more shallow. We're looking at kind of shallow soil failures. It's impacting a much smaller area, but still potentially quite damaging and quite deadly. And you know, if you look at this compared to the Milford example, you'd say, okay, these look like they could be more regular occurrences in rainstorms, but in terms of the magnitude of the events, it's quite different. On the right-hand side here, again, we're back on the Milford Road in Fiordland, looking at a big debris fan. So here we've got a kind of channelized debris flow. You can see it comes from two different headscarps. So we've got a headscarp on this side here and one here, into a very clear debris track into the channel, and then it's obviously over a very long time formed this huge fan, and it's still got an active section on one side. So when we're trying to understand, again, hazard and risk, trying to look at these things, these actual geomorphological processes in the landscape really give us a good understanding of the kind of mechanisms that have caused them and the kind of risks they could kind of pose into the future. We also don't need landslides to move particularly quickly to be a problem. So we can have slow-moving landslides, and they don't have to move very quickly or very fast to cause a lot of damage. This example here is called the Utuku landslide. Again, it's a New Zealand example, and it's just slowly creeping through time. It continually moves, and as a consequence of that, it continually damages the road and the railway line. So State Highway 1 is just running here. That's on the North Island. The railway line is next to it conveniently, but not because of the landslide. And then the landslide is obviously moving all the time. So slow-moving landslides are also a big problem, and understanding how they could move in the future and what kind of events are required to reactivate them is really important. And another thing to be aware of is that a vast majority of landslides are incredibly complicated. They're very complex. So so far we looked at kind of classic examples of different styles of landslides, but many don't really fall into that kind of category. So on the left-hand side here, we're looking at the Dorset coast, and you can see you've got these bench features. So you've got a coastline down here at the bottom, and you've got a rear scarp right back up here. So you've got this rear scarp with these bench features. So you've got this really big, deep-seated landslide system, this complex that's moving over time. But on top of that, because it started moving and it's behaving in a certain way, the upper materials are moving as mudslides. So it's destabilized the whole system, and now we've got these kind of mudslides that form these lobes and debris flows that are coming down over the top. So understanding the kind of hazards that are happening here and the impacts they're having requires you to understand all these different complicated mechanisms that are operating at the same time. And they can work on different time scales and different spatial scales. So it's really quite a challenge. On the right-hand side here is another place that I've worked. This is in Shetland, and these are peat hills. So these are called peat slides. Sometimes they're called bog bursts, depending on the mechanism through which they failed. But what this is really showing is you've got this really clear set of blocks at the top where it started to fail. So you've got this kind of headscarp around here, and then these lateral sides to it. And what's happened is you've got peat sitting on a kind of rocky surface. Water gets underneath that and almost like makes it buoyant and lifts it, and it rafts these blocks, and the blocks start to move. But the critical thing here is very quickly that the mechanism is changing. So it's changing from this sliding block into this kind of slurry. And landslides can do this. Lots of landslides can do, they can change their mechanism quite quickly. So we can go from sliding to some kind of flowing kind of mechanism quite quickly. And that really changes how fast it's moving. It really changes how far it could move and what kind of track it might take. So in this example, you mobilize these blocks. As they start to break down into a slurry, they end up in river channels, and they become these channelized flows. And they can do a lot of damage. They can break culverts and these things. So yeah, it's really important to try and understand the kind of mechanisms through which these things fail and how they change through time. Another thing to mention is that landslides can start cascading hazards. So they can start as a landslide and turn into something else. This is a site that I studied in New Zealand on the South Island in the Southern Alps of New Zealand. It's on the west coast, and anybody knows about New Zealand, the west coast is incredibly wet. so it has huge amounts of rainfall, and as a consequence, it's an incredibly active mountain environment. And the reason we went to look at this was actually because there was a hut here that had been damaged by a flood, and this big flood had ripped out all the sides of the banks, and it had taken all the paths that get you to this hut. And this was a Department of Conservation hut where people go and kind of tramp or hike and then stay overnight. So they wanted to know if they could reopen. They wanted to know what had happened and how to reopen the hut. But this flood basically had destroyed the whole of the Wanganui River. It had come down and it had taken out the bridge, which was one of the state highways, State Highway 6. So State Highway 6 was completely closed, and there's only one state highway on the west coast. So incredibly big problem in terms of diverting traffic. And so we really wanted to understand what happened. And what we found when we went above the hut and looked at what had happened, we got to the top of the Alps to a place called Mount Evans, and the top of the mountain had basically fallen off as a big rock avalanche, but it had fallen in two directions. So the largest section had fallen into what's called the Evans Glacier to the south, and to the right it had fallen into what's called the County Glacier to the north. So these two blocks had fallen off and hit on top of the glacier. In terms of the Evans Glacier, it kind of broken up and moved down a long way. So this pink track is the avalanche flow path. It blocked the river and caused a bit of a lake, and then that lake basically burst the dam that it had created. So it suddenly had a huge amount of water coming out of this dam, shooting down this river. So as a consequence of the way the two different parts of the landslide failed in different ways, one caused a major disruption all the way down the Wanganui River and took out a bridge and a fiber optics cable, and the other sat up in the county stream, and no one probably would have known it ever happened. So they can really cause a lot of hazards further downstream. And a key thing to really understand is that so far we've really talked about individual landslides, but a lot of events are multiple landslides. So we have events that generate lots of landslides in one go over a certain area. And one of the best examples of this, I think, is probably the Kaikoura earthquake, which happened in 2016. So I just thought I'd explain what happened in the Kaikoura earthquake, just starting from the earthquake itself. So I've got a little YouTube video of the actual earthquake, a model of the earthquake. Oh, can I? Oh, that's because that doesn't just. What is it playing? Right, there we go. This is a model someone put together after the earthquake, of the earthquake wave. So it's a magnitude 7.8 earthquake, so very big. It starts in Culverton at a depth of 15 kilometers. You can see it's quite a small earthquake. It actually ruptured 13 faults. So the first fault ruptures and it starts to create this chain of rupturing, and you can see the ground shaking. So the red is up to about 0.5 meters a second velocity. The white is 0.7 meters a second as the ground shaking. So really high ground shaking. So you can see that it's starting to rupture all the way up the coast of the South Island of New Zealand. Then it gets really complicated and starts going in different directions. So just here on the south coast is Wellington. So about 1 minute into the earthquake, Wellington starts to get shaken. Starts to wake up at about 12:30 at night. And it's still going 1.5 minutes now. It's been shaking for 4, and that's, the waves are still going. So this was a huge, huge earthquake that ripped all the way along the east coast of the north section of New Zealand's South Island. And I think by the end of it, I think I saw that the South Island had moved 35 centimeters or something closer to the North Island. That's the kind of amount of energy that was, we're talking about. So a huge earthquake. And obviously this happened in a very mountainous environment, quite close to a coastline where you've got really steep coastal cliffs. So as a consequence of this, the earthquake produced 18,000 landslides. So the map here on the left-hand side is the ground shaking. The amount of the ground shaking, which you can see is associated with where the faults have ruptured, and the energy has gone towards the north. The map in the middle with the pink and the green dots is all the landslides, where all the landslides happened along there. And some of these were really quite big. And we had 196 of these were valley blocking landslides. So they were so big that they basically blocked a valley. So we had 196 of those, which is the black dots. So this picture on the right here basically shows the main area of landsliding and the total area that was damaged by landslides in the earthquake. So a huge event, but a real opportunity to understand a lot more about landslides in earthquakes. And a key thing as well is that, as well as all the landslides, there's areas that don't fail but do get damaged. So you have all this cracked ground, you have all this new damaged ground that's now got kind of big fissures and tension cracks in it, which is really now much more susceptible to failure than it was before. It's really easy for water to get into the ground and cause landslides. So we have this huge damaged environment by the earthquake. So the impacts of the landslides were quite severe. I mean, the first thing was that this happened along State Highway 1, which is, I guess, the equivalent of the M1 in New Zealand. We had huge amounts of landslides all the way along that coastline from Kaikoura all the way up to the north, which basically meant there was no access down that state highway from where you get off the ferry in what's called Picton, all the way down to kind of Christchurch and the other major cities in the South Island. So they're completely cut off. The only way is to go around onto the west coast, which takes, I think, about 6 hours longer. So everything now has to go a completely different route because there's absolutely no access at all. In the event, luckily, it was really late at night. So amazingly, there was no fatalities on the road. If it had been in the day, it could have been quite a different event in terms of fatalities. But there were people that were traveling at that time on the road who got stuck between these major landslides. So suddenly they're now stuck on the road. No one can get to them because the landslides have completely, they stop all emergency services being able to move. So Kaikoura effectively gets cut off. The roads are closed to the south and the north. So the only way in and out, and the only way to get people out who are trapped is via helicopter, which is quite a logistically difficult thing to do. And luckily, the population is relatively small here. It could have been quite a bigger population. Again, it could have been quite a different thing. But the state highway stayed closed for a very long time. It took about a year to get the northern section, the main section, back up to the North Island open. The South Island, they got open much quicker. So I think the earthquake was in March. So by Christmas, they got that section open. But it cost a huge amount of money. There was nearly every geotechnical engineer in the country would seem to be working on this, trying to get this road back open as quickly as possible. So it was estimated that it spent about $2 billion on repairs for the road. The other thing is, next to the road, again, a bit like in the North Island, they've put the railway line. So the railway line is gone with the road. So you've got no rail either. So when you think about the cost of things now, suddenly we're trying to move food and goods and services. Most of that goes on rail or by road. The costs now to move anything are astronomical and much slower. So the impacts start to kind of become much bigger and bigger. And we had things like relocation of sea colonies and properties evacuated due to rockfall risk, because obviously now there's these rocks perched over houses as well. But thankfully, like I said, there was no landslide-related deaths, which was quite amazing. And one of the really big things that happened in the early part of the earthquake response was trying to understand what was going to happen with the landslide dams. So we had these huge dams now in the landscape. They basically block the river. You get a huge lake starting to form behind it. You're flooding everything upstream of it. Downstream of it, you've got potentially people, assets, and you've got this dam. And a really key question is, what's going to happen to that dam? Is it permanent? Is it going to fail? And how quickly could it fail? Is it going to be a burst? Or is it going to slowly erode as we get storms? So a huge amount of resource then has to go into trying to understand the risk of the dams, trying to model the possible ways the dams could fail, deciding and determining whether they need to move people out of properties. And again, thankfully, most of the areas downstream had very few people. It was farm areas, so it's a very small population to make decisions. But it's quite easy for these things to happen in areas where you've got much bigger populations downstream, and making those decisions to evacuate people is not trivial. It's a really big decision to make. And another thing to think about with the earthquake was, because it was along the coast, actually only half of the earthquake shaking was affecting the terrestrial environment. A lot of the earthquake shaking was happening in the marine environment. So we may have not got as many landslides as we'd have expected because a lot of it is offshore. But one thing that did happen was we had this huge event in what's called the Kaikoura Canyon. So the Kaikoura Canyon just sits just off the coast of Kaikoura. It's a really steep shelf, and it's got a really kind of impressive marine environment, quite a unique marine environment. And it was kind of quite lucky in a way. NIWA, who were like the water marine kind of scientists in New Zealand, happened to have done a big survey of that canyon because they're interested in its biodiversity. And they'd done it quite recently, so they had a really good bathymetric survey of the canyon. And they happened to be out when the earthquake happened somewhere else with their boat, and they managed to relocate it to basically survey the canyon to see what had happened. And what they found was this tremendously big flushing event had happened. So the canyon had just flushed sediment out of it. So in that process, the biodiversity is really heavily impacted. Most things, didn't survive. So you have a huge loss of biodiversity. But in a marine environment, you can really fluidize things, and they can move really fast. So the sediments travel really long distances through this thing called the Hikurangi Channel. So the landslides start to really complicate the earthquake and really change the spatial area which is actually being impacted, which is quite an interesting thing. And what was really interesting in the canyon is actually the recovery of the environment was incredibly quick. So there was a lot of concern about how long it would take for this marine biodiversity to come back, but it was actually incredibly impressive how quickly it actually recovers from this kind of event. So we get submarine landslides as well. And another key thing is obviously then there's a tsunami risk. We've shaken the seabed and we've caused landslides on the seafloor, so there's a tsunami risk. So immediately after the earthquake, people in coastal locations have felt long, strong shaking. So their thinking now is I need to get from low ground to high ground. So at 2 o'clock in the morning, they're packing their cars and they're heading as high as they can, waiting to see what happens with the waves coming in. So, an incredible event that's quite frightening. And the final thing to say about these kind of events is what we found, which is really challenging, is that the landslides don't all happen straight away. They don't all happen in the next big storm event. So what we've done is we've effectively reset the landscape, and it takes time for it to get back to the kind of environment, the kind of hazard and risk that we'd have had beforehand. So what we found in Kaikoura was, and lots of other earthquake sites, is that the threshold, the rainfall threshold for landsliding that we'd expect landslides to happen is now changed. So you don't need as much rain to cause landslides. So if that happens, the return interval of the storms that you require to make landslides happen is more frequent, so your risk has gone up. So this is an example of, on the left-hand side, there was a landslide above the road in the earthquake, which is just it's a big landslide, but it's sat up in the hill and nothing's happened. And then during a post-earthquake rain event, ex-tropical cyclone that had gone over it, we get a much bigger landslide than we actually had in the earthquake. So understanding how long that risk stays and how to manage that is really challenging. So you've got people trying to get the roads open as quickly as you can, but you've got potentially a decade of higher hazard to try and manage in your landscape. And of course, these landslides are also going into your catchments, into your river channels. So they're affecting the sediment budgets in your rivers. And again, so now we've created a much wider earthquake problem, and now we've created a much longer earthquake problem on top of that with landslides. So that's why they're so important to try and understand better and study. So I just thought I'd spend a little bit of time talking about some of the research, some of the things that particularly I'm more interested in, I guess, in terms of landslides. And when we look at landslide research, we kind of think of this triangle of how to understand kind of these kind of bigger ground model type behaviors. So the idea is that we have things like site investigation and ground description and interpretation, and we have kind of like mapping and the spatial side of things. We need to also kind of build kind of conceptualized models. So we need to try and model things and understand how they move. But one of the big areas is really in looking at the behavior of soil and rocks, looking at how the actual materials within the landslides behave when they're put under the stresses that happen in these big events, and trying to understand how the landslides form and happen. So some of the work I do really uses advanced shear testing to try and replicate the different conditions in different types of landslides, and really trying to explore how they could fail and how they fail, if that makes sense. And I guess the simplest way of thinking about how a landslide works is that it's this balance of forces. So you have this slope, and you have a series of forces that are trying to that are acting to make the slope move downhill. We call those the shear forces. So we've got forces that are trying to push the landslide downhill. And then you've got these resisting forces. So you've got forces acting that are trying to stop the slope moving. So we call the soil resistance, I think it's resisting this gravitational push on a hill, is basically the soil or the rock's strength. So we're looking at the kind of strength. And when we think about a surface forming, we think of that as a shearing. So we get a shear surface and a shear. So we're thinking about the shear force and the shear resistance acting. And we can think about a landslide as a balance between these two stresses. So we've got a resistance on the top of the equation and a force on the bottom. And when the force is higher than the resistance, we're out of balance and a landslide can happen. And in the laboratory, what we can effectively do is we can go into the landslide. We can take materials from the shear zone, from the place where we think it's shearing, and then we can basically replicate really complicated stress conditions inside the landslide in our machines, and then we can try and put through the kind of events that we think could happen in this kind of controlled environment, and then we can start to measure how that material behaves, so how it deforms and how it slides, whether it moves quickly or slowly, whether it generates water pressure as it's going. So this is an example of some of the machines I use. This picture here on the right-hand side is of something called a dynamic back-pressured shear box. So in here we can put a sample from the ground. We can put a stress on top of it, which basically gives us a kind of burial depth. Then we can set a stress acting at horizontal to that. So we get the kind of push that we're expecting in the slope. So we're getting some kind of initial stress condition that we think is representing what's happening in the earth. And then we can replicate earthquakes and we can replicate rainfall events by changing either the amount of water that's being pushed in, the water pressure, which we do through this volume controller, so we can push water pressure into it, or we can dynamically shake horizontally and vertically the material. So we can replicate earthquakes going through the material, and then as those events happen, we start to see the shear surface form, and we measure that as movement, as displacement, as it starts to break, and we can look at how landslides fail. I hope that makes sense. Simplest way I think I can describe it. So one of the things we've looked at is things like slow-moving landslides. So again, going back to the Utuku site that I talked about earlier, because it sits in this area of New Zealand with lots of these types of landslides, there's 1,172 landslides mapped that are similar to this Utuku landslide. It's incredibly important to understand how they behave. And because there's so many of them, there's kind of a lot of questions of whether they're formed by earthquakes or whether they're formed by kind of long-term rainfall and slow moving. And trying to understand how they're going to behave is a real challenge. But because this one is on the road and it's constantly a headache, it's constantly monitored. So it's had a really good monitoring system put in. So we've got a really good relationship of how it moves. We know how it moves and when it moves. And we can look at things like, whether it was raining at the time to try and understand what's happening in the ground to understand the movement. But what we tend to see is it has these different phases of movement, and every now and again it has these episodic little periods of acceleration before it stops moving again. So it kind of slides and then slows down and slides and slows down. And what we found is that effectively that tends to happen when the water pressure in the ground is much higher, which makes sense. So after big storms, the groundwater table increases and the water pressure in the ground is higher. That makes the material more susceptible to sliding. And we get these periods of acceleration, and then as the water pressure drops again, so as the water dissipates and the pressure drops, we see it start to decelerate. So because we've got this field monitoring, we can try and replicate the same thing in the laboratory and see if we get the same behavior. So on the middle there is the laboratory, and the right-hand side is the field monitoring. And what you can see is that we can replicate pretty accurately what's happening in the ground with our machines. So we can start to actually create events that we haven't seen and try and start to forecast perhaps how the materials might behave and how that might affect the landslide. So one thing that we've done, which was really useful, is then to say, well, what happens when we get really strong ground motions through the landslide? Because we know that there's been earthquakes of kind of 6.2 that have happened in the area, but unfortunately those have happened in a historical period where we haven't had that kind of monitoring, so we can't see how the landslides have responded. So what we can do is we can go to like an earthquake catalog and look at all the possible events over time and start to kind of model how the landslide would work in kind of numerical modeling approaches. But in the laboratory, you can also take those types of earthquakes, put them through the material and look at how the material moves. And what we found is that we can take a numerical modeling approach and our approach, and we get broadly the same behavior. So we start to find that what happens is when we get earthquakes, depending on the size of the earthquake, that dictates how out of balance your forces are during that period of time, and that dictates how far the landslide's going to slip. So as a consequence of that, we can then go and look at how far the landslides move and say, well, how much of the movement is related to earthquakes and how much of the movement is related to rainfall, and how worried should we be about future earthquake events in terms of how far this could move and what kind of damage it could do. So it's quite a powerful approach. Another thing we can do in the lab is look at things that are really hard to study in the field. So one thing that we know from landslides is they don't always have to have a trigger. They can just kind of happen through time. An example is Mount Cook. I can't remember what year this was, but Mount Cook, the top of the mountain fell off Mount Cook, which is the highest mountain in New Zealand, and now it's slightly lower than it was before because the mountaintop fell off. But there was no trigger, there was no earthquake, there was no rainfall event. It just happened. And it was a catastrophic failure. It really fell fast and ran out quite a long distance. So we kind of know that what happens is materials get damaged through time, and that damage can slowly, progressively create a situation where the damage starts to take over, and it progressively fails without any change in condition. If that makes sense, without anything trying to push it. So we can look at that. It's hard to look at that in the field because it's hard to find places that are barely moving and then monitor them for long enough to see how they fail. But we can start to do that in the lab quite effectively. So this is an example of that kind of experiment. So we've taken a material and we slowly increased the pore fluid pressure that's being applied to it in a machine. And then we've basically measured the displacement over a very long time. So this is days along the x-axis, displacement and pore water pressure. So this is what we're applying, this water pressure, and the black is the movement of the material, the deforming shear surface. So what we did in this experiment was we were basically slowly pushing up the water pressure, and as soon as it started to creep, as soon as the material started to move, we just hold the pore water pressure constant. And then we'd wait until the creep stopped, and then we'd slowly increase the water pressure again and again. And it took well over a year to do this. It was kind of a really slow creep test. But what we found right towards the end, it started to creep more and more. So we can see these progressive movement patterns happening. So we held the stress constant for over 80 days. And eventually we see this propagation of cracks, crack propagation behavior, this movement. And then eventually it ran away without any change in stress. So it really shows you that we can understand how progressive landslides happen using lab equipment. And another thing we can do in the lab is we can look at landslides that we can't really get to and we can't really study in great detail. And one of the ones that I've been really interested in and worked on is giant seafloor landslides, so submarine landslides. This is just an example of one of the biggest ones. This is the Storegga landslide, which is just off the coast of Norway. And this is a really big landslide, 280 kilometers long, total volume of 3,500 kilometers cubed. And when this, there's evidence of tsunami deposits when this moved all the way along the Norwegian coast, along the Scottish coast. So in Scotland, I think there's evidence of up to kind of 4 meters above current normal tide level, so tsunami level. So understanding how these big giant landslides on the Sleaford move and the tsunami risk that they could generate is really important. The difficulty is it's really hard to study them. It's really very, very hard. I don't think there's ever been an attempt to try and monitor how they move. So doing that is really difficult. So one of the landslides we've looked at is just off the coast of Gisborne in New Zealand. It's called the Tuahine Landslide Complex. And it sits on the subduction zone off the coast of New Zealand. So we know it experiences really big earthquakes. And it's a really interesting landslide because it's not disappeared. It's still there. It's still this preserved landslide on the seabed. And as a consequence of that, it's had a lot of interest, international interest from IODP drilling. So people have drilled through it to try and understand how this landslide behaves and moves on the seabed. And because they've drilled through it, then we're able to get samples from where we think the base of the landslide is, so we can study it in the laboratory. So one thing that we were really interested in looking at was, well, you know, if it's sitting on the subduction zone and it's very old, it's going to experience quite a lot of earthquakes. And if it's still here, we need to try and understand how a big earthquake hasn't completely caused this thing to evacuate, or, you know, could it evacuate in a big earthquake? And if it moves that amount of sediment that quickly, you know, what kind of, you know, that would potentially be a tsunami risk to the Gisborne coast. So we need to understand this. So what we did was we took a series of earthquakes from around the site that we knew of. And we got basically the earthquake waves to understand how the ground from that earthquake would have, how the ground at the landslide would have shaken during those earthquakes in terms of the amplitude of shaking, how much it shook, and the duration, how long it shook. And then we also looked at the subduction zone, which we've never, thankfully, got evidence. You know, we don't have an actual wave from that because it hasn't happened in the time that we've had the monitoring systems, thankfully. But there are models of that. So we've got the modeled stress drop and the modeled earthquake wave from what would happen if there was a magnitude 8.3 earthquake along the subduction zone. And then we've taken those and looked at that in the laboratory to see if we can try and understand how the landslide could move. And what we found was that effectively you need very long, high shaking to make this landslide move. That's because the landslide's on a really low angled slope. It's 2 degrees. So it requires a really big stress change for it to be able to mobilize on such a low angled slope. So what needs to happen is it needs to shake long enough and hard enough to basically generate high amounts of water pressure so that the water builds up and it can't escape. And effectively, it becomes almost like, you know, the water pressure gets so high that it effectively becomes this kind of flowy, slidey kind of surface that can then slide. And what we found is that the only kind of duration and magnitude of earthquake shaking that would really fit that kind of behavior is subduction zone earthquakes. So our conclusion was that effectively in a subduction zone earthquake, the landslide kind of translates as a kind of conveyor belt, and as soon as the earthquake stops, it stops again, which is a kind of explanation of how we think it behaves. So I just wanted to quickly finish on the UK, really. So obviously we've talked about kind of much more active environments in the UK. But just to say, landslides are also a problem here. There's over 18,000 landslides in the UK in the BGS National Landslide Database. That's the British Geological Survey's database that they keep. And by far and away, I think some of the most active and big ones are on our coastline. So this is Black Ven. Top left here is Black Ven in Dorset. This is the Holbeck Hall landslide in Scarborough in the 90s. This is Ventnor on the Isle of Wight, which is a huge undercliff with an urban population living on it, which is interestingly, because it's been so wet this winter, it's actually reactivated in multiple places. So Ventnor's having a bit of a reactivation at the moment and causing quite a lot of damage. And this again is on the Dorset coast, one of the recent kind of more cliff-style failures, more traumatic cliff failures that's happened along the Dorset coast. So our coastline is very active. And that makes sense when we think about what's happening at the coast in the UK. So this is really where the energy of the ocean and the energy of the atmosphere all kind of meet in a pretty small band along our coastline. So we have this beach, which I guess works as something of a shock absorber. But you know, with climate change and sea level change, you know, we can expect that this is where we're going to see some of the most active environments along the UK coastline. And you know, this is having real significant impacts. So this picture here over on the left is Folkestone Warren. That's the railway line at Folkestone Warren. It's a landslip there. So Folkestone Warren is another one of these big complicated landslides with a railway line on it, which I think has gone through multiple stabilization schemes. Here in the middle is on the undercliff on the Isle of Wight, you know, the road network being damaged. This is up in Yorkshire, where old ancient landslides started moving and started damaging properties. So, you know, we've got lots of transport links, we've got infrastructure, commercial and residential property, and we've got, you know, really important environments on our coastline that are all potentially impacted by landsliding and coastal landsliding. And if we think about what's going to happen in the future, how could the climate impact our coast? Well, we know that sea level is rising, and that sea level is rising globally, as in this figure here. But we also, you know, we know that we've got certain areas in the UK with sea level rise. So as sea level rises, you know, we expect to see more of that energy being forced onto our coastline that we haven't seen for some, you know, we haven't really seen. But in addition to that, we've got climate change. So we're getting things like warmer seas, increasing storm intensity, increasing rainfall, and more unpredictable weather patterns that we don't really fully understand. And I think those impacts are going to be felt really hard on the UK coastline. And as I say, we've got these big landslide systems, complex landslide systems, and we really don't know how they're going to respond to that, which I think is really quite interesting. So this again is just a classic landslide. This is in Dorset. This is Black Ven. And again, you know, you can see all these complicated landslides, and there's a real question: is how will these landslides behave in the future with our changing climate and sea level change? You know, when we've got these different types of landsliding mudslides, and we've got these big deep-seated systems, I don't think we really understand how that's going to change. But we really do need to understand that if we want to try to understand, you know, the kind of hazard and risk that these could pose to kind of beach users and property owners and things like that. So I think this is a really interesting area for future research. I think that's it. Thank you very much.